We often think of logistic regression as nudging the line to improve. But that intuition is incomplete, because most of the time we can't actually see where we're going, and we have to use nearby clues to navigate. But the clues we get depend on the landscape we're navigating. Some landscapes are arduous and deceptive, where a single mistake makes the ground jump beneath you. Others become suddenly barren flat land, and no matter how we nudge the line, we can't seem to improve. Nudging the line is only half the story because it's the outcome of navigating a landscape of possible lines. Peering into that world lets us understand exactly why the line gets nudged the way it does. This is how I think about logistic regression. In this dataset, we're trying to find what distinguishes students that passed from those that failed exams. That tipping point between passing and failing is a line representing a relationship between study time and exam length. For example, 1 study time minus 2 exam length plus 3 equals 0 is one such line, which clearly makes mistakes. But by changing the numbers in front of study time and exam length, we can rotate the line. And by changing the third number, we can shift the line. Together, these 3 knobs allow us to steer the line to a better spot, making fewer mistakes. But how do we know which way to turn each of the knobs in order to reduce the number of mistakes made by the line? So we know how steering works and we know our destination, but we don't yet know how to navigate. But why do we even need to learn to navigate? We can just survey the landscape by exploring all knob combinations and keep track of the number of mistakes. For example, if we turn knob 1 and keep track of the number of mistakes as we turn the knob, we get this curve. But this is just a slice of a larger landscape. Freezing knob 1 and turning knob 2 now, we see a similar slice appear. By systematically incrementing one knob and turning the other, we can gradually map out the landscape of mistakes these 2 knobs would simultaneously create. But there are 3 knobs, and every small change to the third knob creates an entirely new landscape, meaning this entire landscape was only a slice of an even larger landscape. Fully visualizing that larger landscape isn't possible, but we can still record the mistakes made by each knob configuration, and eventually we might just stumble upon the best line. But that's like searching every street one by one, hoping to eventually stumble into your destination. There are simply too many possible lines. So instead, we need to navigate intelligently using local clues. Navigating is about taking in our surroundings and making an educated guess as to where to go next. By turning each knob a little bit, we can glimpse the landscape of mistakes and decide how to best steer the line. For example, let's fix knob 2 and 3 in place and only focus on knob 1. We can turn it a little bit to the right and a little bit to the left, and keep track of the number of mistakes. The curve is flat, meaning that the number of mistakes didn't change. We need to broaden our horizon and look a bit farther out if we are to see where to go next. We'll turn the first knob by an even greater amount. Now we can see a staircase-like pattern emerge. Every stair is a jump in the number of mistakes. Since we want a line that makes the fewest possible mistakes, one way to navigate is to follow the staircase down, which we can do by turning the knob to the left. Now we take in our surroundings again, and repeat. A good place to stop is when the staircase starts to go up in both directions. But this is just the first knob. Steering involves moving all knobs simultaneously. But there's a catch. Each of these staircases assumes all other knobs aren't moving. So as soon as we move one knob trying to improve the number of mistakes, that might completely change the staircases for the other 2 knobs. So at this particular knob configuration, turning knob 1 and 2 to the left would be best, but if we turn knob 1 first, the change to knob 2 is a guess based on prior information that is no longer necessarily reliable. But think of it like blinking. A quick blink is usually fine because you don't expect your surroundings to just suddenly change. Most likely, if we only turn knob 1 by a tiny amount, the curve for knob 2 won't suddenly become drastically different. So moving by small amounts keeps our local information more trustworthy. But there's still a deeper problem hiding here. Navigation is challenging because the landscape only changes occasionally. Small movements often don't tell us anything at all, which means we have to look far just to reveal the few staircase steps we need in order to navigate. Think of it like navigating in New York City. If the streets are extremely far apart, you may walk for a long time before realizing you chose the wrong direction. The feedback arrives too slowly. And that's exactly what's happening here. We spend a lot of effort navigating just to get tiny pieces of useful information. But we're doing the best we can with the information we have. The issue isn't how we're navigating the landscape, the issue is the landscape itself doesn't provide regular enough feedback. For example, if we put New York City on a slant such that increasing street numbers are always uphill, you'll always know where to go. Changing the landscape means redefining what we mean by a good line. The number of mistakes focused on distinguishing students that passed from those that failed. But logistic regression also assigns confidence to its predictions. And if logistic regression is 99% certain a student passed but they actually failed, that's bad. What we're looking for ideally are probabilities that match up with how the student performed. Students that passed should receive high probabilities of passing. Students that failed should receive low probabilities of passing, which also means high probabilities of failing. So instead of counting mistakes, we can combine together the probabilities assigned to what actually happened. We can take all the probabilities of failing for students that failed and all probabilities of passing for students that passed, and sum them all up. A good line should get a score close to the total number of students. A bad line would get a worse score. What's great about this score compared to the number of mistakes is that this sum changes continuously as the knobs change. Even tiny knob movements slightly change the probabilities assigned to students, which slightly changes our evaluation of the line. If we repeat the process from earlier, this time the landscape looks drastically different. Instead of staircases, we now get smooth curves, meaning tiny knob movements always provide feedback. And that feedback is way more reliable because it's smooth and doesn't suddenly jump up or down 3 stairs. And now we don't have to look as far in order to navigate, and we can take bigger steps more confidently. Notice too that not all these curves are the same. Some are much steeper than others. A steep curve means you get way better return on investment. A tiny change to this knob means a big change in how good the line becomes. So why not leverage that information too so that we can change each knob relative to how much better the line might become? If the curve is steep, leap. And now we can navigate much more effectively. But there's a subtle catch. Flat curves can be deceiving. In this particular case, the individual curves for knobs 1 and 2 look like we're close to doing the best we can. But if we look at the landscape of all knob 1 and 2 combinations, we see there's a ridge that appears in a diagonal path. By turning knob 1 and 2 simultaneously, we can walk that path up and keep improving the line. But that's not something the individual knobs were able to see. Which makes sense. When the line is positioned in this way, if we only turn knob 1, it'll mess things up. So it's not that the plots are unreliable, it's that they can only partially see the landscape. What's worse is, sometimes we can get stuck in the moment of our greatest need. If we happen to start exploring the landscape very far from our destination, the landscape here looks flat. Similar to the staircases, it's not really clear where to go, and the lack of steepness in the landscape is telling us to please take small steps, when in reality we should be leaping. Why does this happen? Moving the line a bit will change all probabilities for the better, but won't exactly have a huge effect on the sum. What we want is a compounding effect where small changes to all probabilities have a massive effect. You probably guessed it, instead of summing all the probabilities, we'll multiply them instead. Another way to look at it is that summing is too forgiving. Now, with multiplication, a single catastrophic prediction can completely change the score. That strong feedback is why we multiply. This product also has a probabilistic interpretation that gives it its name, the likelihood function. But navigating this landscape introduces a new challenge. Small probability differences can create enormous likelihood differences. Some tiny nudges barely change the landscape at all, while others create massive jumps. And similar to the sum of probabilities, when we're far from the solution, the landscape can still appear frustratingly flat. But unlike the staircase and sum of probabilities, the issue here isn't necessarily that useful clues don't exist or disappear. It's that tiny local clues become overshadowed by enormous changes happening elsewhere in the landscape. So we need a way to enhance these small clues and slightly dampen the larger ones. Instead of changing the landscape itself, we'll just compress its vertical scale, so that the mountains stay in the same place, but the terrain becomes much easier to work with. This is the landscape logistic regression works with because it's so reliable to navigate. The landscape is smooth, providing quick feedback, and if our starting point is far from the solution, the landscape will be steep, pushing us to turn the knobs more drastically to improve the line. Interestingly, because we rotated the line out of place, it makes sense that this landscape becomes steep. It's telling us that the best correction is to aggressively turn knobs 1 and 2. But if instead we shifted the line far from the data, rotating the line now no longer helps very much, and the landscape reflects that. The feedback from knobs 1 and 2 becomes almost flat. The meaningful correction is to shift the line back into place using the third knob, and that's exactly where the landscape becomes steep. Nearby clues become strong precisely in the direction that meaningfully fixed the mistake. So turning the knobs isn't just about moving the line into a better position, it's about navigating through a landscape of possible solutions. Depending on how we frame what we're looking for, the landscape might become arduous, deceptive, and suddenly barren. Or, like in logistic regression, it could be a well-marked path. In the next video, we'll make these ideas more precise using math. We'll learn to shrink the field of view down to a single point, and measure exactly how much each knob should move. We'll also discover that not all steep directions are meaningful. Sometimes a curve looks promising, but it might just be because we measured study time in seconds and exam length in hours. But the hard work is behind us. We already understand how logistic regression works. The math will just help us make it precise. See you there.